Section 2.3.3, modeling underdamped motion. When we have a specific case where zeta, which is always going to be greater than 0, is less than 1, we have a complex conjugate pair roots that are the solution of the characteristic equation, and we have an underdamped motion case. So that gives us lambda 1 is equal to negative zeta omega n plus omega n, the square root of 1 minus zeta squared j. Sorry, the j is outside the square root. And we have lambda 2 is equal to negative zeta omega n minus omega n square root of 1 minus zeta squared j. These are our two solutions, right? We can pull the j out because the square root of 1 minus zeta squared j is equal to the square root of 1 minus zeta squared negative 1, right? Which gets us the square root of 1 minus zeta squared with the j on the outside. But you can also just trust me. Whatever works for you. Okay. We're going to wing it again. We like winging it here. We're just going to arbitrarily define something that we think might work as a solution, right? Been going so good so far. Why change it out? We're going to introduce omega d is equal to omega n, the square root of 1 minus zeta squared j. Sorry, that is not right. 1 minus, there is no j, right? So 1 minus zeta squared. And that is our damped natural frequency. And if we do that, we get lambda 1 is equal to negative zeta omega n, which is the natural frequency of our system, plus omega d j, where omega d is the frequency that our damped system oscillates at, and omega n is a system where our on-damped the frequency that our on-damped system oscillates at. Lambda 2 is equal to negative zeta omega n minus omega d j. Again, we have two solutions, and we have a linear problem. So a linear problem means that we combine these solutions into one, and we're just going to assume our solution a to the e lambda t works again. Well, that's what we assumed initially, right? So I can get x of t is equal to a1 e to the negative zeta omega n t plus omega d t j plus a2 e to the negative zeta omega n t minus omega d t j. So that gets me a solution, but man, is it long, right? There's a lot of things that we can pull out of that. So I can just pull out that x of t is equal to e to the negative zeta omega n t multiplied by a1 e to omega d tj plus A2 e to omega d, minus omega d tj. So that gets us to something a little bit easier to comprehend. If we think back to Euler's equation, we can choose that capital A1 is equal to A1 minus A2. I'm going to put those in brackets, J. And capital A2 is equal to A1 plus A2, J. Oh, sorry, there's no J on that second one. That's just A2. The J is just on the first one. So we can look back at those. Those were defined, if you're interested, in 2.72. It's equation 2.72. And we can put those into a general form, right? So a general form for this solution is going to look like x of t is equal to e negative zeta omega n t multiplied by A1, capital A1, sine of omega dt plus A2 cosine of omega dt. All right, and again, we have a general solution. The general solution gives us the correct answer, but it's generalized, right? It's good in a mathematical sense. It's not good in an engineering sense. In an engineering sense, we want something that we can just plug values into and that we can think about in our brains, right? To help us understand, like visualize what's going to happen. So now we've got sine and cosine terms. We like this. This aligns better with an engineering perspective, but we still have these capital A, these two capital letters, which can be kind of hard to account for, right? So we can expand this out. If you remember from before, from the 1 degree of freedom, we showed that, I'm going to put this in blue because it's kind of coming back from memory here. X of t is equal to a sine of omega n t plus phi. Remember that? Is equal to a1 sine of omega n t plus a2 cosine of omega n t, if you remember that. Okay. If I look at those two equations, what I have is something that's very similar. The only thing that I have different is I have a damping coefficient and I have omega d. So we can just linear systems. We can linearly superimpose solutions, and I can get x of t, and this is an important one to write down, is equal to a e negative zeta omega nt sine of omega d now, because we're damped, t plus phi. And that's a very important one to write down. So that is a solution in parameters that we can easily get of our equation of motion, right? Okay, we need to get boundary conditions for this, right? And again, we get those by setting everything to 0 and solving out, right? So again, think that x naught and v naught, so we can apply those boundary conditions and we can solve out for terms that give us what we need. So x naught, let's draw it like this. X of 0 is equal to x naught, if I put 0 into sine, omega dt is going to go to omega dt is going to go to 0. So I'm just left with the sine, and the t on top is going to become 0. E raised to the 0 is 1, and so I'm left with a sine of phi. Pretty simple, right? So my x naught is a sine of phi. If I know my x naught, if I know my phase, I can pretty easily, and my amplitude, I guess, I can pretty easily get the other one. We can take the derivative product rule, right? So that's blue is just kind of thinking back to calculus. That's FG prime is equal to F prime G plus FG prime. And if we apply that to our equation that we have, we end up with this is a long one, x dot of t is equal to negative zeta omega n a e to the negative lambda omega n t sine of omega d t plus phi plus a e to the negative zeta omega n t omega d cosine of omega d t plus phi. So that's quite a long one. There are a few things that we can pull out to simplify and just set things into 0. If I just set x dot, so x dot of 0, that's v naught, and I can just start canceling things out, right? So I get negative zeta omega n a to the sine of, again, t equals 0. So to the sine of phi plus a, again, t equals 0. You put 0 up top. E to the 0 is 1. So I'm just left with a omega d. That's not going anywhere. And now I'm going to be left with cosine of phi. Okay. So if a, from before, we showed how we can relate a, phi, and x naught together. So if we let a equal x naught over cosine of phi, we can cancel out a few more things, right? So I've got an a term, and now I've got a cosine of phi on top and bottom. So this is about to get beautiful. I get x dot of 0, which is equal to v naught, is equal to negative zeta omega n of x naught over sine of phi multiplied by sine of phi plus x naught over sine of phi multiplied by omega d cosine of phi. Now we have our classic sine plus cosine. So we can simplify that a little bit with cotangent, and I get x dot of 0. Again, we're just solving for velocity, so we can call it v naught, is equal to negative zeta omega n x, well, hang on, x naught plus x naught omega d cotangent of phi. Which sign do you think should be cosine?
You stated A is x naught over cosine phi, and then in parentheses, place of A in the x naught equation, you actually lift x naught over sine phi in place of A.
So you think both of those should be... No. So, okay, I do have a mistake. X naught is A sine phi. This should be sine. How about that? Does that help fix the problem here? Oh, and that's what it is in the notes. Okay, is that right now? Yeah. The notes are right. So, I transcribed them. Thank you. Okay, so again, I want to put this all into an expression to try to get phi out on its own. So I've got a cotangent of phi in both. So let's throw the cotangent on the left. Cotangent of phi is equal to v naught plus zeta omega n x naught over x naught omega d, which is helpful. And because tan phi is 1 over cotan phi, I can get my phi on its own. So phi for a damped system is equal to tangent inverse of x naught omega d, which are all things that I can easily obtain, over v naught plus zeta omega n x naught. And if you don't write much down, write that one down. Because that will get you your solution for an underdamped system. Okay. From trigonomic relationships here, I can take phi here, which is a very important value, and I can put v naught plus zeta omega n x naught plus x naught omega d. And again, we're just building off of our inverse tangent that we solved for right above in the red square. And that means that my long side here can be the square root of v naught plus zeta omega n x naught squared plus x naught omega d squared. Right? So if we just look at this expression now, if we just look at this expression, we can pull out a term, right? These are all related, sine, cosine. So now we can not define a term, but we can pull out a term, sine of phi. Again, we're just using the triangle to draw it out. Engineers, we like pictures. Sine of phi is equal to x naught omega d over the square root of v naught plus zeta omega n x naught squared plus x naught omega d squared. And we can apply that to get A equals x naught over sine phi, which we had discussed before, right? And now I can get you A equals the square root of v naught plus zeta omega n x naught, that whole term squared, plus x naught omega d, that whole term squared. This whole thing, over omega d. That's a perfectly good expression. A slightly easier way to write it might be, if you want a big square root, you can have x naught squared plus v naught plus zeta omega n x naught over omega d, close out your parentheses, square it, and then you have a nice expression for A that, again, if you don't write much down, write that down. And now that will easily allow you to solve in the time domain for an underdamped solution, because we have an expression for x of t, we have an expression for A, we have an expression for phi. And all you need is your v naught and your x naught. So if you know your initial displacement and your initial velocity, you can solve at any moment in time for where your mass is along your defined axes.